Virtual Metrology Part 2, Deploying the Model. Last lecture we built one and it looked good. R squared of 0.88, error a third of a nanometer and close to the physical noise floor of the metrology tool. Today we changed nothing about that model, same features, same algorithm, same 465 wafers. We change only how we ask whether it works. The answer changes enough that model stops being worth deploying. 6 things by the end of today. Name 2 ways a random split leaks information and split the data so it cannot. That is the first segment and it is the most important thing in the 2 lectures. Derive the error floor a model faces when its own training labels are measurements. It is a direct application of the Gauge RNR equation from the SPC lecture 3. Decide what a model is allowed to do, given how accurate it actually is, accuracy as a permission slip rather than a score. Tune a run-to-run controller for a signal noisier than metrology. Explain why closing the loop destroys the data the model are trained on. That one catches the good teams and it is subtle. And design the control charge, the retraining trigger and the rollback plan that a deployed model needs. One sentence hold all of that together. A virtual metrology model is a metrology tool made of software. Everything today follows from taking that literally. Here is where we finished. PLS, 8 components, 465 wafer labels, 5-fold cross-validation. R squared of 0.82 in 1, RMSE of 0.333 nanometers against a gauge floor of 0.222. This is the real number and honestly computed by standard procedure. Nobody cheated, it is what Skylern returns from the default settings and it is what most papers in this area report. Today the same model, same data, same features, the only thing that changes is the question. And everything that follows from one decision made in one line of code, shuffle equals true. This is the whole lecture, one keyword argument. Segment 1, validation done right. And I want to be precise about where the fault lies. The model was fine, the features were fine, the algorithm was a sensible choice. The question we asked was wrong and a wrong question produced a confident wrong answer with no error message. Let's look at exactly what 5-fold cross-validation did. We start with 465 wafers in round order organized into lots. 25 wafers per lot processed one after another in the same chamber on the same day. Then we shuffle. Every wafer gets random position and we cut the shuffle sequence into 5 folds. Here is the result. Blue is training, gold is test. Look along the row. Wafers from lot 1 are in the training fold and in the test fold. Wafers from lot 5 are in the both. Every lot now appears on both sides of the split and the run order is gone entirely. A wafer from the end of the year sits next to the wafer from the beginning. This is the default in every library. Shuffle equals true is what every tutorial uses, and for independent and identical distributed data it is exit right. It removes any accidental ordering in how the data was collected. Wafer data is neither independent nor unordered. So the shuffle destroys 2 things at once and we will take them one at a time. Leak 1, the same lot on both sides of the split. Here is one lot, 25 wafers under a random split, 5 of them landed in the test fold and 20 in the training fold. Those 25 wafers share a great deal. The same carrier, same queue, same time, same incoming lot measurement, the same operator, the same shift, the same chamber. And in our feature table, all of that lives in the lot level block, 20 columns that are identical for all 25 wafers. So when the model predicts one of the 5 test wafers, what does it already know? It has already seen 25 wafers with exactly the same lot level feature it has seen in their measured CD. It does not need to predict anything, it just needs to recall. And here is how much that is worth. The gray histogram is the total spread of CD across all 465 wafers. The teal histogram is what is left after you subtract each wafer's own lot mean. Knowing the lot mean explains 92% of the variance in CD. 92%. So a model that has effectively been handed the lot mean starts with almost all of the answers and it has to do very little real work to reach R squared of 0.88. A random split hands the model that answer. In production, every lot is new. And you have already saw the evidence for this. I put it on a slide and asked you to hold on to it. Lecture 1, slide 34. The first PLS component leaned hardest on the lot level block F40 through F59. And 7 of the 10 largest lasso coefficient came from the same 20 columns. At the same time, hold that thought. Here is why. A lot level fixture carries no information about the individual wafer. It is a constant across all 25 of them, and what it identifies is the lot. And after a random split, the other wafers from that lot are sitting in the training set with their measurement attached. So a coefficient on the lot level feature functionally is a lookup key. Notice the shape of what happened. The feature that made the model look strongest were the features that made the evaluation invalid. Those two facts have the same cause. That is the unusual pattern, and it is why the unusually good result deserves suspicion before it deserves a celebration. When something works better than you expected, find out why before you tell anyone. Leak 2. Training on the future. Random 5-fold again. Gold is test and look at the positions. Gold wafers are scattered throughout the run order. So for any test result, there are training wafers on both sides of it in time. That model fitted using wafers process after the wafers it is being asked to predict. Time order split in seed, train on the early run, test on the later ones. The model only ever sees the past. Why does that matter? Because a fab is not a stationary process. Chamber get cleaned, parts get replaced, recipes get edited, products change. The relationship between sensors and CD in March is not the relationship in September. A shuffled evaluation lets the model learn in September and the score itself on March. That is not a capability it will have on the day it goes live. Every prediction you make in deployment is a prediction about the future made from the model fitted on the past. The shuffled evaluation never once tests that arrangement. So it produces an estimate of an ability of the model that does not have. And in our data, the process genuinely did change. Here is the demonstration. We trained the model on wafers before the chamber clean at run 600, holding out the last 20% of that period. So both panels are honest. Neither of these is training data. Held out wafers from before the clean, RMSE of 0.454 nanometers, point scatter along the diagonal reasonably well. Wafers from after the clean, same model, no retraining, RMSE of 0.681 nanometers, half again as bad. And look at the pattern. The cloud has pulled away from the diagonal. The clean stripped the polymers from the chamber wall. The wall condition affects the effective chemistry, so the mapping from the sensor reading to the CD moved. The sensors still work, the wafers are still fine. The model's understanding of the relationship between them is out of date. This is exactly what the shuffle hid. Under a random split, wafers from both regimes were in the training and both were in test. So the model learned from some average of the two relationships and was scored on the same average. The clean is in the events file with the timestamp. The information you needed was sitting in the maintenance log the whole time. Two splits that cannot leak. Both are two lines of codes and both should be your default. Group by lot, scikit learn calls it group k fold. You pass lot ID as the group. Each wafer on a lot lands in the same fold, so the model is never asked about a lot that it has already seen. And the principle generalizes well beyond wafers. Use it whenever rows share anything. A lot, a carrier, a wafer, a patient, a user, a session. If two rows share a source of variation, they must not straddle the split. Order by time. Train on runs on 1 to k. Test on runs after k. Then advance k and repeat. This is forward chaining or rolling origin evaluation. This is the only scheme that answers the question deployment actually asks. Given everything up to now, how well will it do next? And when your data is both grouped and ordered, which fab data always is, do both. Group by lots and order by time. The cost is that you get fewer, larger folds and noisier estimates. That is a real cost and it is worth paying because the alternative is precise estimate of the wrong quantity. So the same model, same 465 wafers, same features, same 8 components, same code. 4 ways of asking whether it works. Random 5-fold, R squared of 0.881, that is last lecture's number. Lot grouped 0.733 0.35, we removed the lookup and 15 points of R squared went with it. Leave one chamber out, 0.5752. Train on chamber A, predict chamber B, and the other way. Time ordered, 0.593. From 0.8281 to 0.593, nothing about the model changed. The model was never good at 0.881 and never became worse. 0.881 was always a measurement of something other than what we thought. The same story in nanometers, which is the most useful unit. Our MSE goes down from 0.333, goes from 0.333 to 0.555. The error the model will actually make is 2/3 larger than the error we reported. And the gauge floor is still around 0.222 unchanged. What moved was the distance to it. Now 0.593 still sounds respectable. 59% of the variance explained. That is a perfectly plausible number, which is exactly why we need one more comparison. Put it back next to the baseline and this time score all three on exactly the same held out wafers, which is the comparison we should have made from the start. The baseline, predict this wafer with the previously measured wafer on the time order test window, RMSE of 0.573 nanometers. The model as we reported it last lecture, random 5-fold 0.333, 42% better than doing nothing at all. That is a result worth deploying, a genuine substantial improvement. The same model honestly evaluated 0.555. 0.555 against the baseline of 0.573, that is 3% better, 3%. So everything from last lecture, the feature engineering, the alignment, the PLS, the component selection buys you 3% over one line of code that ignores the sensors entirely. Now the 3% is not nothing. On a well-run wafer, 3% reduction in prediction error might be worth having. But it is a completely different conversation from 42%. 42% justifies a project, a team maintenance burden. 3% probably does not. And I want to be clear about what it does not mean. It does not mean virtual metrology is a bad idea, and it does not mean the work was wasted. The pipeline is right, the features were right, PLS was a sensible method. What it means is that this particular dataset at this label count with this much drift does not support the model we hoped for. That is a finding. It is an honest and useful finding, and you learn it in week 3 of the project instead of month 9 of 1. The best outcome of an honest evaluation is often the project you decide not to. One more question that deployment will ask, and it has a surprising answer. You have a fleet, 2 chamber here, 20 in the real fab. Do you build one model or one per chamber? One model per chamber sounds obviously right. Each model matches its own chamber exactly, no mismatch to worry about. It scores worst, 0.576 nanometers. Because it has your labels, 465 wafers split across 2 chambers is 230 each, and at the count, the model is worth in every way that matters. In a 20 chamber lab, it would be 23 labels per model, which is nothing. One model on all the data lot grouped, 0.497 better because it has all the labels even though it averages over the chamber difference. Train on chamber A and apply it to chamber B, 0.447, and add a simple per chamber offset, one number and mean difference, it improves to 0.438, the best of 4. So a shared model plus some small per chamber correction beats both extremes. We keep all the labels and you absorb the mismatch with one parameter. Splitting the fleet feels safer and costs more than the mismatch does. Measuring it before you decide, and note you only found this out because we ran the leave one chamber out split. Now let us talk about how you report the error, because R squared has been doing a lot of work in this lecture and deserves some criticism. R squared is a ratio, the variance you explained over the variance there was, which means it depends on the denominator. Run the same model on a period when the process happened to be more variable and R squared goes up with no change in the actual accuracy. Run it on a well-controlled period and R squared falls. So R squared tells you about the data as much about the model. Nanometers do not have that problem. Here are 4 quantities on one axis. The specification window, USL minus LSL, 4 nanometers. That is what the designer allows. The process spread, 6 sigma, 5.64 nanometers, wider than the window, incidentally, which tells you this process has a capability problem quite apart from everything else we are doing. Twice the prediction error, 1.11 nanometers, that is roughly the interval within which the true value sits. And twice the gauge noise, 0.44 nanometers. Read those against each other. The prediction error is about 28% of the specification window, and it is about 2.5 times the gauge noise. So quote two numbers every time, error as a function of the specification window and error as a multiple of the gauge noise. The first tells a process engineer where the model is useful. The second tells them whether it can be improved. R squared tells them neither. Let me now consolidate segment 1 into a checklist you can apply to any project in this course and after it. What do rows share? If any two rows share a lot, a wafer, a carrier, a maintenance cycle, anything that they must not straddle the split. Group on the coarsest shared unit. When in doubt, group more coarsely than you think you need to. Does the time run through it? If the data has an order, the process drifts and evaluate forward. A shuffled estimate is an upper bound you will never see again in production. What did you feed before splitting? Scalars, imputers, feature selection, PCA. Every one of them must be fitted inside the fold. If you standardize using the mean of all data, then split, the test set has contributed to the training. It is a small leak compared to the two we saw today. It is present in an enormous amount of published work. Will deployment look like your test set? Each new chamber, new product, new quarter. If deployment differs from your test set in a way you can name, build a split that mimics the difference and report it. That is what leave one chamber out was. And if the honest answer is disappointed, report the honest number. It is the one that is going to happen. Reporting it early is the cheapest possible time to find out. Reporting the optimistic number buys you a few good weeks and then much more worse conversation at a point when people have committed budget. Segment 2, the noise floor. There is a number below which no model can go on this data or any data like it. And it has nothing to do with the model, the features, or the algorithm. It comes from a piece of arithmetic you already know. Here is the observation, and it is one of those things that is obvious once said and easy to miss for years. Your training labels are measurements. The navy line is the wafer's true CD, whatever it physically is. The gold curve is the CDSEM, what the CDSEM reports when you measure the wafer. Sigma of 0.22 nanometers, which we established in the gauge R&R study. 3 gold dots, 3 measurements of the same wafer landing in different places. So when your training set says this wafer is 45.31 nanometers, that number is a true CD plus a random error of 0.22 nanometers, which is lecture 3's equation pointed somewhere new. The observed variance equals the process variation plus the measurement variation. In lecture 3, we applied it to the process, applied to the target column. A model can at best predict the true CD exactly. It can never predict the gauge error because that error was generated independently after the physics inside the metrology tool. So even a perfect model misses every label by exactly the amount the gauge missed it. RMSE minimum equal to sigma gauge equals 0.22 nanometers. And the corresponding ceiling of R squared, 1 minus gauge variance over observed variance, which comes out to 0.948. 2 consequences worth writing down. First, if you ever see R squared above 0.948 on this data, you have a bug or a leak. That is a diagnostic. Second, the gap between your R squared and 0.495 is the only part you can improve by modeling. If you are at 0.94, stop, there is nothing left. You are at 0.5. If you are at 0.59, There is a great deal left, but now you know precisely how much. Your metrology tool sets the ceiling on your machine learning. Improve the gauge and you raise the ceiling for every model you will ever fit. Let us use that to split the error because variances add and two contributions separate cleanly. I've plotted the mean squared error rather than RMSE because the squared error is what adds. Gold is the gauge contribution fixed at 0.22 squared, the same in every bar. Navy is what is left, which is the model's own error. Under random 5-fold, total RMSE of 0.333, the gauge 0.22, model 0.25, roughly half and half. Under lot group, the total of 0.497, gauge 0.22, model 0.446. Under the honest time order split, total 0.555, gauge 0.222, model 0.510. The gold block never moves. It cannot be modeled away no matter what you do. So everybody asks whether a better algorithm would help. The honest answer is a better algorithm can attack the 0.510 nanometers of model error and cannot touch the 0.22 of the gauge error. And this reframes where to spend effort. If your model is already small compared to the gauge error, more modeling is the wrong investment. Buying a better gauge or averaging several measurements per wafer raises the ceiling for everything downstream. That is an argument you can take to somebody who controls a budget, and it can be an argument that comes out of a variance decomposition rather than out of preference. Now a way of thinking about accuracy that I would like you to adopt. Accuracy is a permission slip. The number tells you what the model is allowed to do. Worse than the gauge, use it for monitoring and for ranking. Chart it, watch for shifts, decide which wafer to send to metrology. Those users tolerate errors well because nothing irreversible happens on a single prediction. What it should not do is put a number on the disposition record, comparable to the gauge within a factor of 2 or so. Now it can feed a run-to-run controller with a discounted gain, and it can drive an adaptive sampling plan. Most deployed virtual metrology lives here. Our models at 0.555 against a gauge of 0.22 is at about 2.5 times the edge of this band. Better than the gauge, this is rare and worth pausing over when you see it, because usually it means the model is averaging away metrology noise that the gauge itself adds. In that case, model can genuinely be more repeatable than the instrument. Now skipping measurements becomes arguable with a monitoring sample retained always. So decide what the model is allowed to do from what it measurably is rather than from what you build it to be. That decision is a safety decision, and it belongs to the process owner rather than to the person who trained the model. Last lecture I mentioned Gaussian processes and said the interval was the useful part. Here is that argument made concrete on our own data. Every test wafer sorted left to right by how short the model is. Navy line is the prediction. The shared band is 95% interval, gold dots at the actual measurement. On the left, the band is narrow. On the right, it is wide. The width comes from how far the wafer sits from the training data in a model's own latent space. A wafer whose sensor pattern looks like the things the model has seen gets a narrow interval. A wafer that looks unfamiliar gets a wide one. Now, does the interval mean anything? Split the test wafers into 4 groups by how confident that model claims to be, and measure the actual error in each group. Most confident quarter 0.432 nanometers, then 0.472, then 0.542, least confident quarter 0.727. Monotone. The model's claim about its own uncertainty is correct. Where it says it is unsure, it is genuinely less accurate. A factor 1.7 between the best and the worst quarters, which means the uncertainty is a usable signal in its own right, and the next slide turns it into an operating decision. You don't need a Gaussian process for this. Conformal prediction gives you the calibrated intervals around almost any model, including gradient boosting, with very few assumptions. It is on the reading list, and it is increasingly a practical default. So let the model decline to answer. The horizontal axis is what fraction of wafer of the model is allowed to answer for. It always answers for the one it is most confident first. At the far right, it answers for everything. RMSE is 0.555 nanometers, the honest number from segment 1. Move left at 70% coverage, RMSE on the wafer is, it did answer, is 0.476. The model got better but doing less. Same model, no retraining, it simply stopped answering the question it was going to get wrong. And the 30% is declined to go where they should have gone in the first place, to the citizen, which converts a fixed sampling plan into a targeted one. The cost is metrology capacity, and that was the constraint we started this whole unit with. So you are trading capacity for accuracy on a curve you can now see, rather than picking sampling rate because it is what you did last year. A model that reports how sure it is can be given a threshold. A model that reports a number alone cannot be trusted or distrusted wholesale. Segment 3. Virtual metrology inside the loop. 4 things you can do with the prediction. I have ordered them by what it costs to be wrong, and I want you to deploy them in that order because each one earns the right to the next. 4 uses increasing risk. Monitor. Chart the prediction alongside the measurement you still take. Nothing downstream depends on it. If the model is wrong, a line on the chart is wrong. This is where every deployment should start, and most teams skip it because it feels like doing nothing. It is not doing nothing, it is how you learn the model's true behavior before anything depends on it. Feed the controller. The prediction becomes the feedback signal on the unmeasured lot. Now a bad prediction moves the recipe, which means it moves real data. The next 2 slides are about doing this safely. Choose what to measure. Use the model's uncertainty to pick which wafer goes to metrology. A wrong prediction costs you sampling efficiency and nothing else, no wafer is harmed. Which makes this the best value for the risk of the 4, and it is the one most often overlooked. People jump from monitoring straight to the control. Disposition wafers release and hold material on a prediction with no measurement. The highest value and the only one of the 4 where being wrong means shipping bad products to a customer. Most deployed virtual metrology lives at level 1 to 3. Level 4 needs a much stronger case than a good R squared, and we will come to what that case has to contain. Use 1. Monitoring. And this is where lecture 3's warning becomes an actual chart. The prediction is gold and the measurement you still take is navy. This is an obvious chart and it is less useful one. It mostly tells you the process is moving around, which we knew. The residual, the measurement minus the predicted. 1 point per measured wafer. This is the model's own control chart. Everything from SPC lecture 2 applies to it directly. The center line is the mean residual. The limit comes from a moving range. Sigma hat equals MR bar over 1.128. The individual chart from lecture 2 because we got 1 residual per measured wafer. And sigma hat is 0.299 nanometers. The 11 points fall outside 3 sigma. Now what does a point outside the limits mean on the chart? It means the model, the metrology tool disagreed more than they usually do. That is the different statement from the process being out of control. The process might be perfectly stable while this chart alarms, and that is precisely the case the chart exists to catch. So run both the charts. The process chart on the measurement and the residual chart on the model. A signal on the process chart sends you to the chamber. A signal on the residual chart sends you to the model. Every deployed model needs a control chart on its residual. That was the sentence from lecture 3, and this slide is what it looks like when you build it. Use 2. Feeding the run-to-run controller, and here is the argument for virtual metrology that actually persuade people in the fab. 2 controllers, same process, same brief, and same EWMA. Gold, real metrology, accurate to 0.22 nanometers, available on 1 lot in 5. The controller updates on those lots and holds the correction on the other 4. Till, virtual metrology, noisier. I call it 1.5 times the gauge, but available on every slot. Gold gives the standard deviation 0.289. Till gives 0.252. More frequent feedback, bit cleaner feedback. And the reason is the dead time we drew in lecture 1 of this pair. The controller that updates every fifth lot lets the 4 lots of drift accumulate before it responds. Reducing that delay is worth more than reducing the noise. That is not unconditional. Push the prediction noise high enough and the noisy but frequent signal loses because the controller starts chasing the model error. Sometime between them there is a crossover, and where it sits depends on how fast the process drifts. So this is a calculation, not a slogan. Run it for your own process and your own model before you argue for it. And notice the whole argument rests on the honest RMSE from segment 1 using the shuffle number that would put the crossover in the wrong place. But when you do close the loop, discount the gain. Lambda for virtual metrology equals lambda for the real metrology divided by 1 plus the square of the noise ratio. If the prediction is as clean as metrology, the ratio is 0 and lambda is unchanged. At 1.5 times the gauge noise, lambda falls from 0.3 to about 0.09. At 2.5 times to about 0.04. That is a large discount and it surprises people. The reason is already in EWMA. That recursion weight, the newest observation against the accumulated history, and lambda is that weight. The noisier observation deserves less weight and the optimal weight falls with the square of the noise because variances go as the square. And if you skip it, the controller chases prediction noise. It sees a deviation that came from the model errors and corrects for it, injects variation into the process that was fine, which is the tampering experiment from lecture 1 on SPC unit with a model playing the part of overeager operator, same failure, more expensive infrastructure. The controller has no way to know that its input change source. Nothing about the signal announces it. You have to tell the controller, and the way you tell it is lambda. Use 3. Let the model choose which wafers to measure. The horizontal axis is what percentage of the wafer you actually send to metrology. The vertical axis is the error across the whole lot stream. Measured wafers contribute the real measurement. Unmeasured wafer contribute the model's prediction. Gold, choose the wafer at random, which is what a fixed sampling plan does. Teal, choose the wafer the model is least sure about. At 30% sampling rate, random gives 0.46 nanometers and uncertainty driven gives 0.398. 4% less error for exactly the same metrology spent. No new equipment, no change to the recipe, no additional tasks, risk for any wafer. You measure the same number of wafers, you just choose them better. And notice the gap widens as the rate falls, which is the useful direction. When the metrology is scarce, choosing well matters the most. Of the 4 uses, this is the one I would deploy first after monitoring. It captures real value, and the worst case of a wrong prediction is that you measured a wafer you did not need to. This has a name, and knowing the name is useful because it connects you to the large literature. Uncertainty-driven sampling is active learning. Measuring where the model is least sure reduces error most per measurement. That is what the previous slide showed. Those measurements become tomorrow's training labels, and they are the informative ones drawn from the exactly the regions the model handles worse. So the sampling plan improves the model, which improves the sampling plan. Over months that compound, and it is a much bigger effect than 14% on the previous slide. Now the failure mode, and it is subtle. If you sample only where the model is unsure, you stop observing the regions it believes it understands. And then when it quietly becomes wrong about one of those regions, you have no measurements there to notice it. Your evaluation set has been chosen by the model, so it can no longer tell you when the model is wrong. So keep a random sample alongside. Roughly 18% chosen by uncertainty, 20% chosen at random. The random 20% is what keeps your evaluation honest. It is also, not coincidentally, the same argument as uncompensated sample 2 slides from now. Use 4. Releasing materials on the prediction with no measurement. This is possible, and this is occasionally justified, and it needs a different kind of conversation from the other 3. The honest error under a time order split on the specific product and chamber in question, not the aggregate number, certainly not the shuffled one. The cost of a wrong release multiplied by how often the error exceeds the margin between the prediction and the nearest specification limit. That is a calculation and it needs the tail of the error distribution rather than its RMSE, because what hurts you is the rare large error, not the typical one. And a monitoring sample large enough to detect the model going wrong before the material shifts, which sets a minimum sampling rate you cannot go below, however good the model is. In practice, a hybrid, a model disposition wafers that sit comfortably inside the specification, where when a large prediction error would not change the decision. Anything near the limit or anything the model is unsure about goes to metrology. And that is a good trade because most wafers are comfortably inside spec. So you capture most of the saving while giving up almost none of the safety. Set the abstain threshold from the cost of being wrong rather than from a percentile of the uncertainty. And revisit it when the product mix changes because the margin to the spec limit changes with it. Now the trap that catches good temps, and it catches them precisely because everything is working. Gray is the process below the controller was switched on, teal is after. The controller is doing its job and the variation shrinks and the process holds target. That is a success, somebody gets to present it. Here is the spread in CD in a rolling window of 60 lots and it collapses. Think about what the model needs in order to learn. It needs to see CD vary and it needs to see the sensor patterns vary with it. That covariation is the signal. The controller's entire job is to remove variation in CD. So the better the controller works, the less signal remains in the data model retrains on. Retrain on that data and you get a worse model. Deploy the worse model into the loop and the controller starts acting on the worse information. And the CD variation creeps back up, at which point the model has some signal again. You end up oscillating around whatever accuracy loop the loop can sustain, and you never see it because the chart you are looking at is flat. And that is the difficult part. The flat chart looks like success. There is no alarm. The residual chart may be perfectly in control while all of it is happening. A closed loop consumes the variation that trained the model. If you do nothing about that, the loop slowly eats its own input. So pay for the data that you need. 3 ways in ascending order on how much anybody will argue with you. Keep an uncompensated sample, small fraction of lot, run without the controller's correction. They cost you a little variation in the whole lot and they are the only lot that will show how the raw process. Log the correction, every controller output stored per lot alongside everything else. Because then the uncompensated value is reconstructible. You know what the process did and you know what the controller subtracted. So you add it back, train on that, no sacrifice lot at all. The cost is nothing except discipline. 1 extra column, and it is very often missing because the controller lives in one system and the historian lives in another. Nobody joined them. Deliberate detethering. A small planned perturbation on the recipe on a schedule, completely standard in process identification, deeply unpopular in fab because you are asking permission to make the wafer slightly worse on purpose. Reach for it when the first 2 are not enough. Logging the correction is nearly free and solves most of the problem. Do it before the loop is closed. Retrofitting it afterwards means waiting for months for enough data to accumulate. Segment 4, keeping it alive. The model was correct on the day it was trained. That is the only day you can be certain about, and then everything in this segment is about the days afterward. Here is what model drift looks like on a chart on our own data. The model was trained on wafers before the chamber clean at 100 at run 600. The limits come from the held out wafers, also from before the clean. So they are the honest limits computed the way lecture 2 on SPC unit told you to compute them from a period when the model was known to be good. Then we ran it forward. Before run 600, the residual 6 inside the limit in the control. The model and the gauge agree as well as they usually do. After the clean, 24 points break the limits and the mean residual moves by 0.21 nanometers. And here is the thing to hold on to. The process never changed. The chamber is healthy. The wafers are fine. The CD-SEM is fine. What changed is that the model's understanding of the relationship between them went out of date, which is exactly why you need this chart and not just the process chart. The process chart would have shown nothing This one alarmed within a few lots. A control chart on the residual is how a model tells you it needs attention. Without it, the model degrades silently, and the first sign is somebody noticing the prediction stopped being useful months later. So when do you retrain? The answer is on events rather than on the calendar. The process does not drift on the first of the month. Cleans preventive maintenance, part replacement, chamber reveals. Each one can move sensor to CD mapping. We watched exactly that happen at run 600. And every one of them already timestamped on the maintenance log. You do not need to detect this. Somebody already recorded them. Any recipe edit, any new product or layer running through the same chamber, the model has never trained on that condition, has no way to tell you so. It will predict confidently on a product that it has never seen. The residual chart from the previous slide, a run rule firing on the residual is the model asking to be retrained. It needs no calendar, no maintenance log. This is your safety net for everybody, events that nobody logged. And underneath all of it, a slow background retrain. Month is typical. It catches drift too gradual to trip a rule, consumable aging, seasonal effects in facilities. Treat that as the floor, not the plan. The maintenance log is the retraining schedule that somebody else is already maintaining for you. Joining to it is one of the highest value things you can do on a virtual metrology project. How much history should a retrain use? Measured on our own data rolling forward through the deployment window. Never retrain, freeze the model after training, 0.5 to 6 nanometers averaged over the window. Retrain on every step on the history, 0.459. The 13% improvement for doing nothing except refitting periodically. This is the cheapest accuracy in the entire lecture. Sliding window of the last 550 wafers, 0.502 worse. Sliding window of the last 80, 0.521 were still barely better than never retraining at all, which cuts against the intuition. Surely recent data is more relevant since the process drifts. It is more relevant, but we only have 465 labels in total. Throw away the history and you are fitting against 8 latent components in 80 wafers, and the variance you add is larger than the bias you remove. So there is a trade-off with two terms. A short window tracks drift and estimates poorly. A long window estimates well and lags the drift. There, where the optimum chips depends on your drift rate and your label count, and on our data, few levels, moderate drift, a long window wins. Which means you have to measure this rather than assume it. And this rolling origin experiment is about 20 lines of code. There is no excuse for guessing. One model or one per chamber. We touched this in the segment 1, and here is the full answer. A model per chamber matches each chamber exactly and divides your labels by the number of chambers. On our data, it scored worse, 0.576 against 0.497 on a single shared model. In a 20 chamber fab, it would be far worse and you would maintain 20 models. One shared model has all the labels and averages over chamber differences it cannot see. Fine when the chambers are well matched. It degrades quietly when one chamber drifts away from the fleet, and quietly is the problem. No single model residual charge is watching the chamber specifically. Shared model plus the part chamber offset, one model fitted to everything, and plus a small correction fitted per chamber refreshed open, 0.438 here, the best of 3. And notice the shape of that solution because it recurs everywhere. A shared representation learned from all data plus a cheap part target adjustment learns from a little. That is transfer learning in its simple form. The same pattern appears as fine-tuning hierarchical models and as multitasking learning with a shared trunk, and it is the pattern that scales to a fleet because adding a chamber costs one offset rather than one model. Share it when what generalizes and adapt what does not. Now the part nobody writes a paper about and which determines whether any of these survive contact with a fab. Run the model in production, log its prediction, act on none of them for weeks. You learn the true drift rate, the true latency, what happens when a sensor drops out, and what happens during a product changeover. All of it before anything depends on the answer. Teams skip this because it feels like decay. It is the cheapest insurance available. Model weights, feature codes, training set, pre-processing, a library version, all of it tied together. Because it eventually asks somebody why a particular lot released in March and that was the model version 4.2 trained on these wafers with this code is the answer. I retrained it few times is not. The previous model won't command away tested. The final fallback usually reverting to the fixed sampling pan, so a failing model degrees service rather than stopping the line. A model with no rollback becomes a model nobody dares to update, and a model nobody dares to update is the one that drifts. And name an owner. When the residual chart alarms at 3 in the morning, somebody gets paged. If that person does not exist, the alarm is a decoration, the chart is still drawn and nobody acts on it, and you have all the cost of monitoring without the benefit. A model with no owner and no rollback is a prototype. Whether the hardware is running is on. Segment 5, and it is short. Everything so far has been about one model predicting one quantity on one chamber. That is the right unit to start with, and it is where I want you to begin any project. But you will hear the phrase digital twin constantly in vendor material, in job description and research proposal, and it is worth 5 slides to say what it actually means, because the term has been used loosely enough to become almost meaningless. The useful version of the idea is this. You have spent 2 lectures building one component of something larger. Here is what it is a component of. Let's start with a real definition rather than a marketing one. ISO published a manufacturing digital twin form framework, ISO 23247, first part in 2021, and its definition is on the slide. I want to read it slowly because every clause in it is doing the work. A fit for purpose digital representation of an observable manufacturing element with synchronization between the element and its digital representation. Fit for purpose. The twin model, what the decision needs and no more. A twin built for run-to-run control needs critical dimension and chamber state. It does not need the plasma chemistry solved from first principles. That clause is doing something important. It licenses you to build something small. Fidelity costs money and effort, so buy only the fidelity that some decision will actually consume. A great many digital twin projects fail by trying to model everything. Observable manufacturing element. That is the thing being twinned, and the standards list is broad: equipment, material, process, facility, personnel, product. The operative word is observable. If you cannot sense it, you cannot synchronize to it, which means the twin's boundary is set by your instrument, not by your ambition. Synchronization. The twin updates as the asset changes and it can send something back. This is the clause that separates digital twin from everything it gets confused with. A finite element model of a chamber is a simulation. A physics model of an etch is a simulation. Both are useful and neither is a twin because neither is tied to a particular physical chamber that is running right now. A simulation answers what would happen to a chamber like this one. A twin's answer what is happening to this chamber right now. Sync is what you are paying for. Everything else on the slide is modeling. You may already know how to do. Here is a reference architecture from the same standard simplified, and I have colored one box code. The observable manufacturing domain, the physical things chamber wafer recipe operator. This is the fab. The device communication domain. 2 directions both matter. Data collection going up, which is the FD system we spent lecture 1 turning into features. Device control going down, which is how a correction reaches the tool. Digital twin domain, look at what sits in it: a state estimate, a physics process model, a run-to-run controller, virtual metrology in gold. The gold box is what you built. Everything in these 2 lectures produce one component of this span, not a small one. On a real edge twin, virtual metrology is often the component that makes the rest of it useful, because it is what gives the twin current value for a quantity nobody measured. And user domain. The process engineer, the dispatcher, the planner, the twin exists to serve a decision somebody makes. If no decision consumes its output, it is an expensive dashboard. Then the loop, data up on the left, decisions down to the right. That calculation is the synchronization from the previous slide, which reframes the whole unit. You do not build a standalone model, you build a prediction component of a chamber unit, and everything from segment 4, the residual chart, the retraining triggers, rollback, is how that component stays trustworthy with inside it. How far the twin extend? This is the question that decides whether a program succeeds, and it usually gets answered by ambition rather than capability. One chamber sensors a virtual metrology model, a run-to-run controller. It predicts controls that chamber. This is what you have been building. One tool, several chamber twins, plus scheduling and preventive maintenance state. Now you can do chamber matching, the shared model plus offset from earlier, and plan maintenance against actual condition rather than the calendar. A process area, tool twins plus work in progress, queue state. Now dispatch becomes the question you can ask the twin. If I send this lot to tool 3 instead of tool 5, what happens to cycle time? The fab area twins plus full product genealogy. Yield attribution, classical planning. And here is the part vendors skip. Each rung needs everything to its left kept alive and in sync. Fab twin containing a stale chamber twin is a fab twin that is wrong, and it will be confidently wrong about the lot you are deciding whether to ship. So the maintenance burden multiplies rather than adds. 40 models is 40 residual charts, 40 retraining triggers, 40 owners. Almost every fab digital twin in production today lives in the first two boxes. Equipment level, the area fab boxes exist mostly as research program and as slideware. Earn each rung before you claim the next, and when somebody shows you a fab twin, ask which chamber the twin underneath it was retrained most recently. What it adds and what it costs, both halves are real. The twin can answer questions you did not ask in advance. Your virtual metrology predicts one number for the condition that actually occurred. A synchronized twin can be rerun with a changed input, a different recipe set point, a delayed PM, a reordered queue, and give you the counterfactual before you commit to it. This is a genuine step up in capability, and it is the honest reason to want a twin. It gives the fleet one shared state. Chamber matching, dispatch scheduling, all need the same current picture of every tool. Without a twin, each application reconstructs that picture for itself from the same raw data with slightly different assumptions, and then they disagree and somebody spends a week finding it out. Now the cost. Every component inherits 4 problems from today: leakage, a noise floor, drift, and nobody is owning it. A twin with 40 models has 40 of each, and the twin is only as current as its most neglected component, which will be the one nobody remembers building. And the integration is genuinely the hard part. One shared state needs one shared vocabulary across tools from different vendors with different data models with different names from the same physical quantity. That metadata problem is larger than any of the modeling problems, and it is why standards like ISO 23247 exist at all. They are an attempt to agree on the nouns. So treat the phrase with the right amount of respect and the right amount of suspicion. The concept is real, the standard is real, and the equipment level version is deployed. A digital twin is a maintenance commitment before it is a capability. Start with one chamber, keep it honest, add a rung only when the one below it has a owner and a control charge. Which brings us back to the sentence this lecture has been built on. So back to the sentence I promised at the start, and it survives the detour through digital twins intact. A virtual metrology model is a metrology tool made of software. So it gets a gauge study. You would never accept a CDSEM into a fab without knowing its repeatability and reproducibility. Characterize the model's error in the same way, honestly split, reported in nanometers, stated as a multiple of the gauge it is imitating. That was segment 1 and segment 2. So it gets the control chart. Every metrology tool in a fab has one. The models is the residual chart, a small sample of real measurement charted against the prediction with limits and run rules. That was the segment 3 and the start of segment 4. So it gets the maintenance schedule. Tools are recalibrated after events on the schedule, so are models. Retrain on the chamber events, recipe changes, residual alarms with a slow refresh underneath. And I like this framing for a specific reason. Everything in a fab already knows how to do with a metrology tool. Qualify it, monitor it, maintain it, own it, transfers directly. You do not need to invent a governance process for machine learning. You need to notice you already have one and apply it. Everything in these 2 lectures follows from taking that sentence literally. Homework, same data sets plus a project prompt. Take your lecture 1 model unchanged and re-evaluate it in 4 ways. Random, lot group, leave one chamber out, time ordered. Report R squared and RMSE for each and explain each gap. You should reproduce the number from slide 11. Compute the baseline on the time orders test with only, not on all the data, which is the mistake that makes the comparison flattering. Then state your model's honest advantage over it. Train on runs before 600 and apply forward, and build the residual chart with limits from the held out pre-kin wafers. Say when it should have alarmed and which run rule should have first. Split your honest RMSE into gauge distribution and model's own. Then answer the question a manager would ask: how much of the remaining error is worth chasing, and what would you do to chase it? Given your model's RMSE, a gauge sigma of 0.22, what lambda should a run-to-run controller use if it uses 0.3 on real measurement? On the line of arithmetic, I want the reasoning. Propose a deployment. Which of the 4 uses what abstain threshold and why? What the residual chart looks like, subgroup limits, which run rules, what triggers the retrain, and what rollback means concretely.